we've got an idea then of the evolution of stars, but now we've got to look at a really big picture. So we've got to look at the whole cosmos and how that's changing. So the first thing we need to understand to do that is the Doppler effect. You'll have mentioned the Doppler effect in GCSE. This is an effect of the movement of the source of a wave, so it could be a sound wave or it could be a light wave. Obviously in this case we're only going to be talking about light waves coming from stars. So an increase or a change in the wavelength of the star depending on its motion relative to us. Okay, it's worth mentioning that it doesn't matter whether the star's moving or we're moving. That's a bit of a moot point. Okay, all that matters is the relative motion between the two objects. Okay, so here's an example. So here's a stationary source, it's giving out a wave. Here's the wavelength, the observer. If both things are stationary, the observer will observe the same wavelength that the source is giving out. But if the source is moving away with a velocity v, then the wave will be stretched. So imagine the source was here when it was made. Okay, in the time it takes the wave to move, the source has moved over there. The extra wavelength, delta lambda, is an increase in wavelength caused by the motion of the source. I've got an animation to show that a bit more clearly. So here's the source giving out a wave. Constant wavelength goes past there. It's the same as the wavelength given out by the source. But if I just take this wave over here so I can put it here, okay, you'll notice that as I move the wave away from the person, what the person's seeing is stretched. So we get a longer wavelength now than the source is actually producing due to its motion. If the source moves towards the observer, then we get the opposite effect, and the observer sees a shorter wavelength than the source was actually producing. So what we need to be able to do is to put some numbers to this, work out how delta lambda relates to v, and we can do this fairly straightforwardly. So what we need to think about is the time to produce one wave. The period of the wave is t. The distance moved by the source in that time will be its velocity times the time. So if it's moving away from us, the increase in the wavelength, delta lambda, will be the velocity times the time, the extra distance moved by the source while it produces each wave. We'll also remember that the period is 1 over the frequency. So another way of writing that is delta lambda is v over f. Okay, we also know that what lambda, the wavelength, is c over f, just from c equals f lambda. So delta over lambda is v over f over c over f. We can cancel out the f's and we're just left with v over c. Okay, the minus sign here is just showing us which way the wavelength will change. So this is an increase in wavelength when the velocity is moving away from us. If it's coming towards us, obviously the wavelength will decrease. Okay, the frequency also changes, obviously, because delta lambda and delta f are not two independent things. We can just use c equals f lambda to rearrange that again and get this equation. We don't use this one so much. But the change in frequency divided by the frequency is also v over c. Just a little mention that all of this assumes that the thing is moving at relatively low speed, so maybe up to 1/10 of the speed of light. This is a good approximation. If you get into relativistic terms, this equation isn't quite the same, but fortunately we don't have to worry about that at the moment. So here's a little application of Doppler shift. This is to binary stars. So here's a binary star system. You've got a big red star and a small blue star, in this case, going round each other. Okay, this is what we call a plan view, so actually you wouldn't see any Doppler shift if the stars were seen to be doing that. Okay, because although they're moving, they're not moving towards us or away from us. Okay, this is what's called an eclipsing binary system. This is where both stars are in the same plane, so they seem to go in front of each other. Fortunately, my animation is not quite good enough to make the blue star go in front of the red star, so the University of Nebraska have kindly provided us with a slightly better animation. So here we go, here's our small blue star going around our big red star. Now this animation doesn't show us about the Doppler shift, but it does show us about what's called the light curve, which is quite interesting. So here's a dip in the light as the binary eclipses. So you'll notice as the red star goes in front of the blue star, there's a big dip. That might seem surprising, but remember the blue star is a hot star, therefore it's actually producing more energy, more power output than the red star. So you'll see a small dip when a little bit of the red star is blocked out by the blue star, but a big dip when the whole of the blue star is blocked out by the red star. Okay, just if you can't imagine how that looks, let me just tilt it for you. This is what's actually going on. Okay, the two stars rotating around each other around their common centre of gravity. Okay, so it's a very powerful animation. You can change all sorts of things on here. It's well worth a look if you've got a minute to have a look at this web address. Okay, so if we apply that to a set of stars, this is what we're going to see from the Earth. Okay, one of the questions I get quite often asked in GCSE is, well, how do you know the light's redshifted? How do you know it wasn't just red in the first place? How do you know this Doppler shift's going on? Well, our old friend absorption lines are crucial for this. So we know the various lines that we'll see in the spectrum, for example, those hydrogen-Balmer lines in the visible part of the spectrum, so we can look for how those seem to move. Okay, so here's two stars, one going around much faster, so this line here that's moving a long way, this star must be moving much faster than the one that's not moving so far. Let's have a look to see if we can work out how fast it's moving. Well, we know the wavelength is centered here at 600 nanometers, so this must have been a 600 nanometer line in the first place, and we can see that it's moving up and down, so it's going this way as it comes towards us by 60 nanometers, this way as it's going away from us. So delta lambda is 60 nanometers. If we rearrange our equation, we get delta lambda over lambda times c. That gives us 3 times 10 to the 7 meters per second. We could do the same thing for the small star. That would tell us quite a lot about the system, the relative masses of the stars, for example. This number's not very realistic because that's obviously very fast. That's a star that's moving at a tenth of the speed of light just around a binary system, so that's not going to be happening. But I just did it like this so you could see this principle quite easily. Here's some more realistic numbers. So here's a line at 434 nanometers, and it's going up and down by 0.15 of a nanometer. So to get the velocity of the star, we just do the same equation, and we get 1 times 10 to the 5 meters per second. But if we combine that with a period of 300 hours, so if it takes 300 hours for the light to do this, again, obviously the animation is very much speeded up, so you can don't have to sit there for 300 hours to watch the line go forwards and backwards. But if it does this, we can also work out the radius of the rotation. So we know t equals 2 pi r over v, so this is the period, is the distance around the orbit divided by the speed. We can rearrange this to get the radius of the orbit as tv over 2 pi. Here's our time converted into seconds, times our velocity divided by 2 pi, and that gives us the radius of orbit of the two stars. So if you combine that with the light curve, if you combine it with the other star, what that's doing, we can find a lot of information on binary systems by using these kind of techniques.